Ohm's law, which is what we finished with last time, is better stated or more popularly stated as a resistance is equal to a voltage divided by a current, or more commonly V equals IR. Resistance is a constant of proportionality between the voltage and current. We use the symbol, the capital Greek letter omega for ohms. That's the symbol for resistance, so that 1 ohm is equal to a volt per amp. And when we talk about circuits, we are most interested in looking at circuits that have resistors in them, at least for this part of the course. Generally speaking, resistors come in many different shapes, but a real popular shape is the one right here, where they can come separate, or they can come on integrated chips. They typically have 4 colored bands on them. The first 2 bands give the resistance value. The 3rd band represents the power of 10. We call it a multiplier band. Then the 4th band is either usually gold or silver. That indicates the tolerance. At 5% tolerance is indicated by a silver band. At 10% tolerance is indicated by a gold band. There's also a resistor code, so that if you see black, the number represents 0, brown represents 1, etc. down the list. And of course the multiplier as well. Brown represents 10 to the first, red represents 10 squared, and so on and so forth. And so that's the way you would read a resistor. So for example, if I had a resistor that had a red, blue, green, and silver band, that would tell me the red and the blue, that's a 2 and a 6 by the resistor code. So it'd be 26 times 10 to the 5th, or 2.6 mega ohms, 2.6 million ohms. The tolerance is indicated by the silver band, that's a 10% tolerance. Resistivity is a quantity that is aligned with resistance. Resistivity, first of all, is measured as 1 over the conductivity. So resistivity has SI units of ohm meters. Resistance and resistivity are related by the following expression. Resistance is equal to the resistivity times the length divided by the area. Resistivity is a characteristic of a material, and we can see a table of resistivities here. You see that metals like silver, copper, and gold, tungsten, and so on, platinum, have very low resistivities. Things like rubber or glass or whatever would have a much higher resistivity. So every ohmic material has a characteristic resistivity that depends on the material, also on the temperature. It's a property of the substance, depends on its geometry and its resistivity when I want to calculate a resistance. And an ideal conductor would have 0 resistivity. Ideal insulator, of course, would have infinite resistivity. If I were to do, and we will do, either a simulated or actual experiment to illustrate Ohm's law, if I were to plot current versus voltage, I would get a linear relationship for ohmic material such that the slope of this line, if I plot I versus V, would give me 1 over the resistance. Oftentimes I have the students plot V versus I, so I get a slope that's equal to the actual resistance of a resistor. But be that as it may, this is one way of describing the linear relationship between voltage and current in ohmic materials. In non-ohmic materials, we see a more of a non-linear relationship. Good example of a non-ohmic material is a junction diode. We'll talk a little bit about them when we do AC circuits. The last thing I'd like to talk about in this sort of preliminary circuit chapter is to talk about power. So we've studied power in Physics 1, and of course power was the rate of doing work, or energy divided by time, and the same thing applies in the case of electricity. So in the case of this, we can illustrate it this way. Suppose I have a circuit with a battery and a resistor in it. If I have the charge move from system A from point A to point B, the charge will acquire a potential energy equal to Q times the potential difference. The battery, of course, will lose that much potential energy, so that energy is conserved. What will ultimately happen is that the potential energy will be transformed into internal energy or heat in heating up the resistor. And that's typically what happens in a circuit. A resistor is a dissipative circuit element. So we also expect that the resistor will emit thermal radiation, get hot. It will get hot during the course of doing a circuits lab, for example. Eventually, though, it will reach some constant temperature. When we talk about the resistor heating up, it will dissipate power, and the way we calculate that is by the product of the voltage and the current. So power is equal to voltage times current. If I use Ohm's law or apply Ohm's law, I'll get three different expressions for power. I squared R, probably the most common way of describing power. V squared over R, or I times V, all of which apply. And of course, the units for power are the same as they were when you studied mechanics. They're watts, or joules per second. Say a few more things about current before we get into actual circuits. If I have one single electron that moves at the drift velocity in the circuit, it may take hours for an electron to move completely around the circuit. But the current is the same everywhere in the circuit. You never use up current in a circuit. Charges flow in the same rotational sense as all the points in a circuit. And finally, I talk about electric power transmission. Real power lines have very little resistance, and we typically find that power companies transmit electricity at high voltages and low currents so that they can minimize their I squared R or power losses. Electric circuits and currents and resistors are a lot more fun when we look at combinations of resistors in a circuit. So, just as in the case of parallel circuits, in circuits with capacitors, we can look at resistors in series and parallel. Let's look at resistors in series circuits. The squiggly lines are symbols for resistors. You've probably already gathered that. Suppose I have the following configuration where I have three resistors connected in a circuit. One of the ways we are able to discern very quickly if a circuit is a parallel circuit or a series circuit is to ask ourselves, does the current have a choice? In a series circuit, the current has no choice. The current can only go one way. There's only one path for the current to follow through this circuit, and that is this way around the circuit. In the case of a series circuit, I can write an equivalent circuit to that. The resistances add. And so the equivalent resistance, in this case, R equivalent, would just be equal to R1 plus R2 plus R3. The current in the circuit would similarly be the voltage coming out of the battery divided by the equivalent resistance. And so let's just put some numbers in and let's see what we can get. What I would like to do, similar to the case of circuits with capacitors, let's find an equivalent circuit where we have one battery and one resistor, and let's find the voltage drops across each resistor and the current that goes through each resistor. In a series circuit, it's really quite simple. Since the current has no choice, the current in this circuit is going to be the same everywhere. And of course will be equal to the voltage coming out of the battery divided by the equivalent resistance. So just as an example, let's say that R1 is equal to 3 ohms, R2 is equal to 2 ohms, and R2 is equal to 4 ohms, and R3 is equal to 1 ohm. So in this case, the equivalent resistance would be the sum of the resistances, and so that would be equal to 3 plus 4 is 7 plus 1 is 8 ohms. The current in the circuit would be 12 volts. Let's say the battery was a 12-volt battery. 12 volts divided by 8 ohms, or 1.33 amps. That means that you would have 1.33 amps going through each of these resistors. To find the voltage across each resistor, then we would apply Ohm's law, V equals IR, and so in each case I can multiply the resistance times the current. That would give me the voltage drop across this resistor, and then for this and for this as well. This would be, of course, 1.33 volts. This would be 1.33 times 4, or let's see, that would be 4/3 times 4, or 16/3. This would be 1.33 times 3, or roughly 10 volts. And if I add the 3 voltages together, I should get 12 volts, which I will get when I add these 3 numbers together, as it should be. So very simple how a circuit in series works. Suppose now, suppose I want to look at resistors in parallel. In series, by the way, notice something. If I break the circuit anywhere, the current will stop flowing. Any break in the circuit, if there is no current flowing through one resistor, there won't be any flowing through the other as well. As I said, the current has no choice. On the other hand, we can talk about resistors configured in a parallel circuit, like so. So for example, I might have a 12-volt battery, and I might have, let's say we have a circuit with 3 ohms, 4 ohms, and 6 ohms. In the case of parallel circuits, the current has a choice. So the current can come from here, and it can go this way or it can go that way. One of 2 choices. Once again, it can come to this junction. We call these junctions. The current can flow this way or it can flow that way. What that tells us is that in a parallel configuration, the voltage is the same everywhere. So the voltage across the 3 ohm resistor is 12 volts, voltage across the 4 ohm is 12 volts, voltage across the 6 ohm is 12 volts. But the currents add, so that the current from the battery is going to be equal to the sum of the currents going through each of the resistors. By that, since V equals IR, the equivalent resistance in the circuit then would be calculated by saying 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Notice the similarity between resistors and capacitors. When resistors are in series, we add the resistances to get the equivalent resistance. When capacitors are in series, we do 1 over to get the equivalent capacitance. In parallel, resistances go as the reciprocal, capacitors simply add. So there's a difference between those two. Other equivalent C's though are the voltage in a parallel circuit is the same everywhere as it is in a parallel circuit with resistors. For a series circuit, the current is the same everywhere for a circuit of resistors. The charge is the same everywhere for a series circuit of capacitors. So you see these two similarities. In this particular case, I can find the equivalent resistance simply by saying 1 over R equivalent is equal to, let's see, 1/3 plus 1 over 4 plus 1 over 6. I get a common denominator that's 12. And so I'm going to get an equivalent resistance that's going to be equal to, so R equivalent is going to be 1.33 ohms. That tells me that my equivalent current would be 12 volts divided by 1.33 ohms. I'm sorry, this is not 12 volts, it's 24 volts. My apologies. 24 volts. 24 volts divided by 1.33 ohms, and that will give me 18 amps. So the currents going through each of those resistors should add up to 18 amps. Let's see if this works. So in this case, the current through this resistor, 12 divided by 6, is 2 amps. The current through this, again, Ohm's law, 12 divided by 4 is 3 amps. And 12 divided by 3, I'm sorry, these should all be 24. My apologies. 24, 24, 24, so this is going to be 4 amps. This is going to be 24 over 4, so that would be 6 amps. 24 over 3 would be 8 amps. 8 plus 6 is 14, plus 4 is 18, and sure, it all adds up. So that's a very nice, a very simple way of finding an equivalent circuit. Once again, we encourage you to draw the equivalent circuits, particularly for more complicated problems. So this would be a 24-volt battery and a 1.33 ohm resistor. What we'd like to do now, of course, just as in the case of capacitors, it's no fun just to have plain old series or plain old parallel circuits. It's a lot more fun to combine them. And we'll do several examples of combinations. Now you'll notice one thing before we do some more examples. Your household is wired in parallel. Because, of course, if you turn one appliance off or you disconnect one appliance, you don't want all of them to turn off. So typically you use a parallel circuit for your household wiring. Things like when people use lights for Christmas trees and so on, oftentimes they're connected in parallel so that if one bulb burns out, the rest of them don't. There are sets of lights though that you can use that are, you can tell they're wired in series because if one light bulb fails, the entire set fails. So that's kind of inconvenient. Let's do then a nice example of combination, series and parallel. So suppose I have a 12-volt battery and I've got the following resistors: 6 ohms, 3 ohms, 4 ohms, and 5 ohms. And the goal is to find the equivalent resistance, draw the equivalent circuit, find the currents through each resistor, and the voltage drops across each resistor. First thing you do, once again, we go as far from the battery as possible. We go to the right. These two are resistors in series, so I'm going to leave the original ones alone. So I have 12 ohms, that's 3 ohms. This is 6 ohms. But now I have a combination of two resistors in series. I just add them. So that's going to give me a 9 ohm resistor. Now I'm still as far from the battery as possible. I have a 6 ohm resistor and a 9 ohm resistor in parallel. And so if I want the equivalent resistance, we'll call that 1 over R parallel is equal to 1 over 6 plus 1 over 9. And when I do that, I'm going to get R parallel equal to 3.6 ohms. So now I have a circuit that has a 3 ohm resistor in series with, in this case, a 3.6 ohm resistor. Finally, the last equivalent circuit, the real one with one resistor in it, is just the series sum of these two. So it's going to be a circuit with a 12 volt battery and 6.6 ohm resistor. The equivalent current for the circuit would be 12 volts divided by 6.6 ohms, which would give me something like 1.82 amps. And then what you do is you work backwards. So if I have 1.82 amps, and these guys are a series combination, this has 1.82 amps, and this has 1.82 amps. I can find the voltage on each of those resistors, multiply 3 by 1.82, and that will give me 5.45 volts. Multiply 3.6 by 1.82, and that will give me 6.55 volts. Of course, these two add up to 12 volts. Now I go back to the previous circuit. In the previous circuit, I have, in this case, I can find the currents in this. So I know that my 9 ohm resistor this is actually a parallel combination of these two resistors. So the voltage across each of these will be 6.55 volts. The voltage across this will be 5.45 volts. The current then I can just get by dividing 6.55 by 6, which will give me 1.09 amps. The current for this guy will be 6.55 divided by 9, which will give me 0.73 amps. And the current here, of course, is 1.82 amps. That gives me all of the voltages and currents for this circuit. So again, that's a nice example of how to calculate voltages and currents for circuits of a combination of resistors. Suppose you have a condition, though, where you have more than one battery, and suppose you can't break a circuit down into a very simple one battery, one equivalent resistance. We have another technique that we can use to solve that. It's called Kirchhoff's rules, and that will be the topic of the next lecture.